Hello everyone, we're RealBot, building a trust infrastructure for AI agents. Today, I'd like to walk you through the service we envisioned using Arbitrum Stylus. On January 28, 2026, an open-source AI agent framework called OpenClaw was released. Within just 72 hours, it reached 60,000 GitHub stars. In only 1 week, it attracted 2 million visitors. On Moltbook, a platform dedicated to AI bots, 1.6 million AI bots were registered, generating more than 7.5 million posts. As of today, OpenClaw has surpassed 190,000 GitHub stars, becoming one of the fastest-growing open-source projects in GitHub's history. These numbers show this isn't a passing trend. They're evidence that the era of AI agents is no longer theoretical. It's arriving fast. However, there's a critical problem. We still lack a clear way to verify the real performance of AI agents doing important work. We can't reliably answer questions like, is this agent actually delivering the performance it claims? Has the code been quietly changed after deployment? Were the reported benchmarks manipulated? Right now, there's no practical way to confirm these answers. And as the agent boom accelerates, this trust gap is growing right along with it. The market has already recognized this problem. When we look at trust in AI agents, the numbers are striking. In 2024, 43% of organizations said they trusted fully autonomous AI agents. But in 2025, that figure dropped to 22%, nearly cut in half. Technology advanced, yet trust declined. This shows a clear reality. Even if agents become more capable, people still hesitate to rely on them. As a result, the AI agent governance market is growing rapidly. According to Next Move Strategy Consulting, the global AI governance market is projected to grow from $620 million in 2024 to $7.38 billion by 2030, with an expected CAGR of 51% from 2025 to 2030. SS&C Blue Prism put it this way: if 2025 was the year everyone talked about AI, then 2026 is the year enterprises start asking, does it actually work? We are shifting from promises to proof. And that shift is happening right now. And that is exactly the problem we're here to solve. We're here to close the trust gap in AI agents. Until now, there has been no reliable way to verify whether an agent's claimed results and its stated performance are actually true. But here's the question the judges rightly raised. Why would a successful bot voluntarily prove its performance? The answer lies in privacy. And that's exactly what ZK proofs enable. First, fund managers. A fund running an AI trading agent wants to attract outside capital. Investors need proof of performance, Sharpe ratio, P&L, drawdown metrics, but the fund absolutely cannot reveal its trading strategies. That's its alpha. With our Stark-based proofs, the fund can prove, my Sharpe ratio is 2.30 without exposing a single trade. Prove your performance without exposing your alpha. That's the incentive. Second, protocol DAOs. DeFi protocols increasingly delegate treasury management to AI agents. But before granting access to millions of dollars, the DAO needs verifiable proof that this agent actually performs. Our certification creates a governance gate. Only agents with a valid on-chain performance badge get treasury access. Third, marketplace users. As the agent economy grows, buyers need a way to compare agents before purchasing or subscribing. Certified performance badges become the trust signal, like a verified seller badge on a marketplace. You might ask, then why not just verify the agent? That's a fair point, but even verification doesn't fully solve the problem. The verification data itself can be manipulated. After verification, the agent's performance can be quietly degraded. And most importantly, third parties have no reliable way to trust verification results from the outside. That's exactly what ERC 8004 addresses, structurally. In simple terms, it's a standard that gives AI agents an on-chain ID card. Each agent gets a unique on-chain identity, and every verification record is bound to the chain. That means anyone can independently check the agent's status at any time. Our solution is built on top of this standard. What we're building is a performance verification and certification platform for AI agents. Here's how it works. First, an agent developer registers their bot on our platform and requests a performance verification. To run that verification, we retrieve the agent's on-chain history and bind the verification data on-chain, so the inputs are tamper-resistant. Based on this bound data, we generate a Stark proof off-chain. Then we submit that proof and verify it on-chain using a ZK Stark verifier. If the agent passes verification, we issue an ERC 8004-based certification badge. This badge is valid for a certain period, and if it isn't renewed, it automatically expires. Critically, the ZK proofs verify performance metrics, like Sharpe ratio and P&L, without revealing the underlying trade details. This is what makes voluntary opt-in rational. Developers prove their edge without exposing it. For revenue, we have 3 streams. Certification fees paid by bot developers, marketplace transaction fees as agents are traded, and DAO integration licenses for governance frameworks. You might ask, why not just store the verification results in a database? The answer is, We can't. At least not if we want real trust. If the data is stored only off-chain, the inputs used in the off-chain proving step can be manipulated. A developer could upload only favorable results and delete unfavorable records. On-chain binding is the minimal trust anchor that prevents this. By committing the root hash of the verification artifacts to the blockchain, we inherit the chain's properties: chronological ordering, immutability, and public verifiability, all at once, thanks to the linked structure of block headers. To make this scalable, we use a Merkle tree. It compresses large volumes of logs into a single root hash and allows us to prove inclusion of a specific item in logarithmic time. So if anyone presents a different version of the records, anyone else can publicly audit it. The records are on-chain, and the chain cannot be altered. For on-chain ZK verification, we chose Starks for 4 reasons. First and second, speed and cost efficiency. Because we must also prove the on-chain binding structure, we need an approach that can go from proof generation to on-chain verification efficiently. With Starks, we can achieve fast proving and verification, and keep gas costs low for AI agent verification. In particular, when using Arbitrum stylus, Stark constructions that work well with Kekkak hashing are especially advantageous for both performance and cost. Third, quantum resistance. Many Snark systems rely on pairing-based cryptography, which is expected to become vulnerable in a practical quantum computing era. Starks, on the other hand, are hash-based, and with appropriate design choices, they can maintain strong security properties in a post-quantum setting. Fourth, no trusted setup. Many Snarks require a trusted setup to generate public parameters. If the secret randomness, sometimes called the toxic waste, is ever leaked, it can enable forged proofs. That dependency on a ceremony is itself a trust assumption. Starks are transparent and do not require a trusted setup, which removes that entire class of risk. Now let me walk you through exactly why we chose Stark over Snark, in terms of both speed and cost. To evaluate an AI agent's trading performance, we need to verify 2,000 transactions. Each transaction requires a Merkle membership proof at tree depth 11. That means 22,000 hashing operations just for membership proofs, plus 1,999 internal nodes, totaling roughly 23,999 Kekkak 256 hash invocations that must be proven inside the circuit. Here's where Snark starts to break down. Each Kekkak 256 call requires approximately 150,000 R1CS constraints. Multiply that across 23,999 hashes, and you land at 3.6 billion total constraints. That's thousands of times beyond Groth 16's normal operating range of a few million. The circuit is simply too large. So what does that mean for proving time? Using a standard benchmark of 15 seconds per 1 million constraints, 3.6 billion constraints translates to roughly 54,000 seconds, about 15 hours to generate a single proof. That is clearly not viable for any real-world certification service. To put the numbers together, 23,999 hashes times 150,000 constraints, plus a small overhead for aggregation logic, gives us 3,599,900,000 total R1CS constraints. At 15 seconds per million, that's 15 hours of wall clock proving time. For a certification system that needs to renew every 30 days, this is a deal breaker. Now let's look at Stark. We used real benchmark data from the StarkNet STWO prover, running on AMD EPYC Rome, 48 cores, 184 GB RAM. 2 benchmarks matter here: SHA-3 chain, which models sequential hashing, and SHA-3 benchmark, which models independent hashing. Much closer to how a Merkle tree actually works. The SHA-3 benchmark is the right model for our case. Using linear extrapolation from the SHA-3 benchmark data points, 1,128 hashes at 59 seconds, 3,155 hashes at 106 seconds, we derive a slope of 24.4 milliseconds per hash. Plugging in 24,000 hashes, roughly 598 seconds, about 10 minutes, on the 48-core benchmark machine. However, there's a memory constraint. STWO's peak memory usage hits 151 GB at large inputs, far exceeding the 32 GB RAM on a C5.4x large instance. Running all 24,000 hashes as a single proof would crash with The solution is to split into 12 batches of DAW 248 hashes each. Accounting for batch overhead of plus 15% and the 3x core slowdown from 48 to 16 cores, we arrive at approximately 34 minutes total proving time. Now the cost. 2,063 seconds divided by 3,600 gives 0.573 hours of compute time. At 0.68 per hour for a C5.4x large on-demand instance, the off-chain proof generation cost comes to approximately 0.39 per proof. Compare that to Snark's 15 hours, which at the same rate would be over $10. Side by side, Stark takes 34 minutes versus Snark's 15 hours. Off-chain cost is 0.39 versus 10.20. On-chain verification is roughly equivalent, about 0.20 for Stark, 0.18 for Snark. Total cost, 0.59 versus 10.38. Stark is 17.6 cheaper, and that gap only widens as transaction volume scales. This chart makes the difference impossible to ignore. On-chain verification costs are nearly identical. Both systems are competitive there. But the moment you look at off-chain proof generation, Snark's bar towers over Stark's. 1020 versus 0.39s. The total cost difference is 17.66. The reason is fundamental. Snark must encode every KEKAK hash into R1CS constraints. 3.6 billion of them. Stark processes the same work as roughly 580,000 trace rows. A linear operation. That's why Stark wins, both on speed and on cost. Starks are an extremely powerful zero-knowledge proof technology, but in a standard EVM environment, verifying Stark proofs directly becomes prohibitively expensive in gas. That's why projects like ZK Sync Era and Polygon ZK EVM can't always use Starks end-to-end. Instead, they rely on wrapping, encapsulating a Stark inside a Snark. In other words, you're forced into a detour. Stark, Snark wrapper, EVM. This increases complexity, adds extra proof generation overhead, and introduces additional trust assumptions around off-chain computation. Arbitrum Stylus is different. Stylus provides a WASM plus EVM multi-VM environment. That means we can deploy a Stark verifier written in Rust directly as an on-chain contract, and even cross-call it from EVM contracts. So instead of a detour, we get a much simpler path. Stark, Stylus, Rust, on-chain. Now let me quantify how effective this is, with real numbers. Using the Poseidon hash, a core operation in Stark verification, as a benchmark. A conventional EVM implementation consumes 86,952 gas. But with Rust plus Stylus, it drops to 11,887 gas. That's roughly a 7x reduction in gas cost. A common approach in the EVM ecosystem is to wrap a Stark proof inside a Snark. But that wrapping step introduces additional trust assumptions. It also means you pay twice on-chain, once for the wrapping cost, and again for the verification cost. On the infrastructure side, it often requires an off-chain coprocessor, and the wrapped Snark portion is not post-quantum secure. With direct verification on Arbitrum Stylus, we don't need any extra trust assumptions. Thanks to Rust-level optimization, we can reduce gas costs by roughly 10x to 18x. And because we call the on-chain contract directly while preserving the Stark structure end-to-end, we also preserve quantum resistance. In short, Arbitrum Stylus is the only environment that satisfies all three of our requirements at once: direct Stark verification, native KEKAK support, and low-cost computation. Some chains use ZK-friendly hashes like Poseidon. Starknet is a well-known example. But we intentionally use KEKAK for three reasons. First, KEKAK is the EVM's native hash function. It is built in at the opcode level, so we can use it immediately and cost-efficiently without implementing an additional hash function. Second, our system uses KEKAK for both the Merkle tree and on-chain binding. And because Ethereum and Arbitrum also rely on KEKAK-based hashing primitives, our verification structure connects naturally to the chain's own state and history. Third, if we tried to import a Poseidon-based ZK stack from another chain, we would need extra bridges and conversion layers. On Arbitrum, KEKAK is already native, so we avoid the bridge entirely and eliminate that overhead. If we look for the closest comparable competitors, there are two. First, Phala Networks DStack proves the agent's execution environment at the hardware level using TEs, specifically Intel TDX. It can guarantee that this code ran on this hardware, but it does not tell you whether the agent's performance is actually good. In other words, it's an execution integrity attestation, not a performance certification. Second, Authentic is a framework for building AVSs on EigenLayer. If you implement the verification logic yourself, it verifies outcomes through state-backed consensus. It's a powerful infrastructure tool, but it is not a service that certifies AI agent performance. In contrast, we are building a complete, end-to-end service. From agent performance evaluation all the way to ERC 8004 certification issuance. With built-in privacy that lets developers prove results without exposing strategies. Right now, there is no player occupying this exact position. For our demo, we chose GMX. GMX is one of Arbitrum's flagship decentralized perpetual futures exchanges. Because all transactions are publicly available on-chain, it's an ideal target for verification. And since it's a core protocol in the Arbitrum ecosystem, it lets us demonstrate the practical value of our solution directly. Here's the flow we'll show in the demo. An agent processes real GMX transaction data and binds the resulting outputs on-chain. Then we generate a Stark proof, and a stylus-based verifier validates that proof directly on-chain, showing the entire pipeline end-to-end. The era of AI agents is here. But the moment agents enter DeFi, trust stops being a minor inconvenience. It becomes real financial risk. Right now, users have no solid basis to trust an agent. and developers have no way to prove performance without giving away their competitive edge. We solve both problems with a combination of 4 components. We anchor records through on-chain binding to establish a trustworthy foundation for proofs. We generate tamper-resistant proofs with Starks. We verify those proofs directly on-chain using Arbitrum Stylus. And we issue the result as a publicly verifiable ERC 8004 certification. This creates a system where you can prove your performance without exposing your alpha. Records cannot be altered, and anyone can independently verify. Infrastructure that makes agents trustworthy. That's what we're building. Next, let me introduce our team members. This concludes our presentation. Thank you.